All right, welcome back. Hello, I got a comment or something. We are at 2012 BC, number 6, I'm assuming, but I'm not quite sure. Okay, it says using the ratio test, determine the interval of convergence for the Maclaurin series. Again, Maclaurin series is centered at x equals 0. So I set it up a little bit. The ratio test is the limit as n approaches infinity of the ratio of consecutive terms. So it's kind of written formally like this, where you have your n plus 1th term, which means like your next term and the previous term. And that's going to equal some L. And the ratio test, you can force it to be less than 1 to force convergence. And so we got the ratio test every time, I think. You can rewrite it as the multiply by the reciprocal. And then you got to just be careful with what you start to cross out, your factors and everything. So the way I do it is I ask myself, which has more terms, the top or the bottom, numerator, denominator. If this is n plus 1 and this is n, this has one more term. And so when we write the next step, I know that all these negative ones are going to cancel out, except there will be one left on the top. Consult your exponent properties if you need help convincing yourself of that. A little bit trickier here, x to the 2n plus 3, x to the 2n plus 1. 2n plus 3 has two more x's than this. You can think of this as x to the 2n plus 1 times x squared. When you multiply, you can add the exponents, and these are equivalent. And so if you think of this as x to the 2n plus 1 and x squared, then these will cancel out, and you're left with an x squared. And then the 2n plus 3 and the 2n plus 2 we'll let hang out for a little bit. And so I'm going to rearrange some stuff and essentially rewrite this as the limit as n approaches infinity. And I'm going to put the n's right here up in front because the n is what we're taking the limit of. And then it's weird to think about it, but I have this 1, which is going to go away, and then I have an x squared. And these are both considered constants because they have no n's in them. And so I had a hard time getting my head around that when I first started doing this. This is a constant because you care about n's. And so this limits, L'Hopital's rule, is just going to be 1, 2 over 2. This is 1, and you're going to end up with an x squared here. Anything squared is already guaranteed to be positive, so you don't need the absolute values. And the ratio test says if we want it to converge, we're going to make this less than 1. So if that's the case, then this is the case. And if that's the case, let's use an absolute value here somewhere. We're going to have this. And that is our potential interval. The radius of convergence, it doesn't ask for it on here, but if it did, the radius of convergence would be equal to 1. That's you can think of that as the distance from the center, which is 0 because it's Maclaurin, to each endpoint. But one thing that we need to do if we want to maximize our points is we technically need to know if -1 is included in this. When you have a strict inequality here, it's technically not included right now. It's saying the number is strictly between -1 and 1. So the last step of this, if you want to maximize your points, is to test the endpoints. Test -1 to see if it actually converges. Meaning, if you think about your series, and your series looks like this, you have x cubed over, x cubed over 3 minus x cubed over 5 plus x to the 5th over 7. And you substitute in negative 1. You get negative 1 over 3 minus negative 1 cubed over 5 plus negative 1 to the 5th over 7. And you simplify this, you end up negative 1/3. Check your signs, plus 1/5 minus 1/7. What you have, man, this can take up a lot of fake paper. What you have here is you have an alternating series, alternating meaning the signs are alternating, and the terms are decreasing. Each one is less than. And there's a test out there that's not used too often, but it's called the alternating series test. And when you have alternating signs and they are decreasing, it converges by definition. That might help you with a multiple choice question too. And so we should have an equal sign here. And then I have to do the same thing for x equals 1. And so if I do that really quick, I'm going to get this, which utilizes the same thing, alternating series, and it's decreasing. And so the final answer for part A, the interval of convergence, with my justification, is negative 1, including the endpoints, to positive 1. All right. I think we just got a bunch of points on the national exam. Okay, part B. The Maclaurin series for G evaluated at x equals 1/2 is an alternating series whose terms decrease in absolute value. So, if you plugged in 1/2 here for x, you'd have 1/2 over 3. So again, I'm plugging this in to these x's. Minus 1/2 cubed over 5 plus 1/2 to the 5th over 7. And they tell us that if you substitute that in for the approximation, because that's what a series does, it's approximation, that the first two terms, not the first three, the first two terms equal, oh my goodness, 17/20. Wasn't that nice of them to add it up for us? Show that this approximation differs from g of 1 over 2 by less than 1 over 200. If you watch my other video on series, this is kind of classic interpret what we want you to do. This is another way of talking about this idea of error. And it doesn't use the word error, but it's saying that this right here, 17 over 120, is an approximation using a series, and they're saying that this approximation differs from the actual function by some amount. We want to show that that amount is less than 1 over 200. A lot of times they'll give you a criteria, less than 1 over 1,000, less than 1 over 100, whatever. In this case, it's 1 over 200. And so, when you're asked to do this, let's go back down here and create some space. So we have this Taylor polynomial that looks something like this. The first two terms, you have this. And if we want to know the error, we want to know the difference between, g of 1/2 and the Taylor polynomial. Sometimes they use a t for Taylor polynomial, sometimes they use a p. And the way to do that is if you are approximating with two terms, you're always, to find error, you're first going to spell error right. To find error, you're always going to look at the next term. So if you want the error of a two-term approximation, you're going to look at the third term. If I wanted the error of a three-term approximation, I would look at the fourth term. And so the error here is I'm going to look at the next term, which is x to the 5th over 7. And I want the error at the point that it talked about. So I believe the point was 1/2. That's your x value. And so if I plug 1/2 in here, I get this. And if I simplify this, it's 1 over 32 over 7, which is 1 over 32 times 7, which is 7 times 3 is 21, 2 times 7 is 14. All right, 224. And we're supposed to show that the error was less than 1 over 200. And so we got a denominator that is greater than 200, and so I have shown that this error is less than 1 over 200. That will give me full credit. And so what's the take-home point is when you're asked about error, you want to use the next term. You want to use the n plus 1th term evaluated at your x to determine the error. All right, and finally, letter C. Write the first 3 non-zero terms and the general term of G prime. I actually think this letter C is easier than some letter C's. And so we've got our G of x, which was equal to x over 3 minus x cubed over 5 plus x to the 5th over 7. And so our G prime is going to be 1/3, just took the derivative of this, minus 3x squared over 5 plus 5x to the 4th over 7 minus ... I can't do much to simplify this. In fact, everything's simplified, I think. But it does ask me to write the nth term. And so we got to look for patterns. I see a couple patterns. You know, we got powers of x are even. We've got denominators as well as numerators are odd. And so some of the tricks with these things is when you're dealing with even numbers, you usually have some version of 2n. When you're dealing with odd numbers, you usually have some version of 2n minus 1, 2n plus 1. In this case, maybe 2n plus 3, depending on what odd number you want to start with. And then when you have alternating signs, you guys have started to see this a lot, you have some version of this to force that to happen. So we got to put kind of some of these ideas together to try to create an nth term. So we'll quickly do this. I'm going to do the alternating signs first. And so if I do -1 to the nth power, if n is 1, it's going to be negative. I want it to be positive. And so we kind of have to decide if we want to use 1 or 0 for n. Sometimes it kind of implies what we want to use. This one starts at 0. And so I'm going to go back down here, and if I say the first term is 0, then if I plug in a 0 here, it'll spit out that. If I plug in a 1, it'll spit out a negative, and so I think this will work. All right, the next thing I want is I want x. And again, I want the evens. And so I think if I just plug in 2 in here, if I plug in 0, it'll be x to the 0, the x will go away. If I plug in 1, it'll be x squared. And so, again, I think that'll work. And so the thing I have left now is I need to represent the coefficients. And so I have 1, 3, 5. And so if I plug in an odd, and if I plug in 0 here, it's 0, and I want to start at 1. And so I'm going to do kind of a 2n plus 1. And again, if I plug in 0, I get a 1. If I plug in a 1, I get a 3. If I plug in a 3, I get a... Why did I plug in a 3? No, if I plug in a 2, it works out. I was worried there for a second. So that's my numerator. And then the bottom, I want to plug in a 0 and have it spit out a 3. And so maybe I try this. Plug in 0, it spits out 3. Plug in 1, spits out 5. And I think, that's my nth term. So, all right, I hope this helped a little bit. Smile. You guys are awesome, and you totally can handle this. So, have a good night. Thanks for watching.